Hi, my name is John Holmquist, and I'm going to talk about my final project today, which I did on predicting house sale prices in Miami. Um, so I had a couple research questions I wanted to answer. And the first one is, can it be predicted based on the characteristics of a house, whether it is above the median price or below the median sale price? So that's a classification question. And the second research question is a regression question. And I wanted to predict, or I wanted to see how accurate regression can be for predicting the actual sale price of a house based on certain characteristics. So the data set I found for this was the Miami housing data set. And I got that using datasetsearch.research.google.com. And it's a pretty good data set. It has a lot of data. So the target variable is, of course, going to be sale price. And the available features I have to use to predict sale price is the lot square footage, the floor area, the value of special features, the distance to the nearest rail line, the distance to the ocean, the distance to the nearest body of water, the distance to Miami Central Business District, the distance to the nearest subcenter, distance to nearest highway, the age of the house, whether or not there's a lot of airplane noise, the quality of the house, and latitude and longitude. So here's just a view of the data frame just to kind of see what the magnitude of those variables are. So sale price tends to be like in the hundreds of thousands. And the land square footage is like 9,000, 12,000, and so on. So there's a lot of different magnitudes and a lot of different features. So for cleaning the data, I wanted to check the features for any NaN values. So I do that in the code snippet on the right. And this data set was really nice. It didn't have any NaNs, so I didn't need to do any data cleaning there. In a second, there will be a histogram and some scatter plots. And from those, it doesn't seem that there are any outliers. Checking for outliers could be one step of data cleaning, but with this, it didn't seem necessary. And then I wanted to pre-process the data. So the values of the different features, they come in a lot of different ranges. And so one feature doesn't influence the model in a way it shouldn't. It's important to scale those features properly. So the way to do that is to scale each feature to have mean 0 and standard deviation 1. And that makes it so each feature is weighted appropriately. And you can see in the code snippet on the right that I do that using the standard scaler. So for data labeling, I have some statistics for the sale prices. So the mean is close to 400,000. The median is 310,000. The minimum is 72,000, and the maximum is about 2.6 million. So you can see in the histogram that the data tends to be clustered around the lower end of prices, but it also doesn't appear that there are any like really true outliers here. So using the mean to divide the data would make the classes unbalanced, and models tend to perform better with balanced classes. So therefore I use the median because that's a better measure to divide the data if I want good model performance. So I created labels for the houses with sale prices above and below the median. And I chose two classes because most classification algorithms work best with binary decisions. You have to do some extra stuff if you want a model to predict more than two classes. So the data was pretty big. There's almost 14,000 entries. So it wasn't necessary to use cross-validation. I could just divide it into a training set and a testing set. So the training set has more than 10,000 data points, and it's significantly larger than the testing set with just under 3,500 data points. So I hold out the testing set, And the model doesn't see that testing set until it actually makes predictions with it. So the code snippet on the bottom left shows creating the labels. And the code snippet on the bottom right shows creating the training set and the testing set. So the first type of model I'm going to develop are classification models. And the way I set this up is where a function will fit and then evaluate the model. And that way I can call that same function over and over again with different feature sets. So in the first step, I just set up the training labels and the testing labels. And then I select a subset of the data. Based on certain features that I pre-selected and passed to the function. Then I do the scaling pre-processing that I talked about a minute ago. And then I'll fit a classification model. So in this one, it's a linear SVM model. But those lines of code are replaced in different functions with different models. And then for classification problems, I'm going to evaluate the model by making a confusion matrix. And I'm also going to numerically evaluate it by calculating the classification rate. I did something pretty similar with my regression models. So up until fitting the model, it's pretty much the same. But when I fit the model, it's going to be a regression model. So this one is a decision tree regressor. And then visually, I'm going to visualize it in a different way. So I'm going to plot the predicted values from the regression model against the actual values. And what I would be looking for is that all the data points lie along the line y = x, which indicates that the model is performing really well. And then I'm also going to calculate the mean squared error, which is a measure of another numerical measure of how good the model is at predicting things. I'm also going to do the square root of that because the square root is a little bit easier to look at, especially with big numbers. And it also tells me kind of what's a reasonable expectation for how accurate the model is. So for feature engineering, there's a lot of features in this data set, and it would get kind of computationally difficult to look at every possible subset of those features. So I picked 10 feature sets that seemed reasonable. So like in the first one, I just look at the square footage of the lot and the square footage of the home. And then I kind of add in other features and try different things. Down at feature set 10, I have almost all the features in there. It actually performed pretty well. It was one of the best performers, but there was so much going on in there. Feature set 6 performed almost as well, with a lot fewer features, and that's a lot more interpretable when there are fewer features without much of a sacrifice in model performance. So all the models that I'm going to show are from feature set 6. So the square footage of the lot, the square footage of the house, the distance from the ocean, the distance from a body of water, the distance from the central business district, the distance from a subcenter, and the values of special features. So down below, you can see how I called those functions earlier to evaluate it on a bunch of different models. So I basically just passed it those different feature sets, and it plotted the results and did the calculations and told me how they performed, and feature set 6 performs pretty well. The first model I'm going to show is logistic regression. So the way that works is it outputs probabilities, and then it uses a threshold to determine the different classes. A pretty common threshold is 0.5. But for classification, this got a classification rate of 84%. Then I also did a linear support vector machine with a classification rate of 82%. And the way a support vector machine works is it creates decision boundaries for classification. There are different types of support vector machines. This one's a linear one with a linear kernel. And that means the decision boundaries are less flexible than if it had a polynomial kernel. And some hyperparameter tuning I had to do here was that when C was set to 1 or 10 or 0.1 or 0.01, the model wasn't converging very well. And it actually converged well when I set it to 0.001. Then the next model is a decision tree classifier. So I got that the classification rate for this is 87%. And decision trees can sometimes be better suited to problems with complicated and nonlinear relationships between features. So at each level of the tree, a decision is made to branch in a specific direction. And then the leaves of the trees end up being the classifications. One hyperparameter I had to tune here was the tree max depth. And the way I did that is I just looked at one model and I tried a bunch of different max depths of the trees and I saw what worked the best. So it ended up that 15 worked pretty well as a maximum depth for the tree. But I think the tree actually stopped earlier at lower depths because the performance was pretty similar, but I gave it the maximum of 15. So now moving on to regression. This is a decision tree regressor that works pretty similar to a decision tree for classification, but it does regression instead of predicting classes. And so here the square root of the mean squared error is about 152,000. And what that means is that we can predict, or we can expect predictions to be within that range of error. Finally, I did a multiple linear regression. And this didn't perform quite as well. The square root of the mean squared error is 197,000. And this works pretty much like linear regression, but with multiple variables. And basically coefficients are found for each feature. And the linear combination of those variables outputs a prediction for the home price. And then for actually visually evaluating these models, what I did is I plotted the points against each other. So the predicted points versus the actual points. And I want them to be as close to the line y equals x as possible. And it's actually pretty good. So it's generally pretty linear here for the decision tree regressor. It's a little less linear with the multiple linear regression, which could explain why the mean squared error is a bit higher. These features, they obviously have significant predictive power about whether a house will be in the upper or lower half of sale prices, but they're not perfect. And there's definitely a trade-off between interpretability of a model and having as many features as possible. So there's other factors to sale price, such as how well maintained the homes are, the school district, and the safety of the neighborhood. So without those features, you can't really expect to have a perfect model. The regression models also work reasonably well. They're not perfect, but with pretty limited data, predicting sale prices within $150,000 to $200,000 isn't too bad. So in the future, I want to use the latitude and longitude coordinates to extract data about the neighborhood from other sources. It could be information like school district and safety and prices of other homes. Some information might be good as categorical, like information about the school district. And a lot of models have trouble with categorical data, but there are ways around it. So like some models like decision trees are good for it. So I deployed my model using Streamlit Cloud, and I wrote the deployed model in Streamlit. So I can actually pull it up here. So here I can see the model is actually hosted on the web. I'm going to go back to the PowerPoint now to finish. So basically, I have the research questions, some training data, testing data, the model type, classification rate, and then a place where you can actually use the model. So you can input the values of the features, and it predicts whether the sale price is above or below the median. And these are my references. And thank you for listening to my presentation.